Okay, welcome to Free Spirit Spheres. This is a little video about a strain test experiment we're doing. Now what I've got here is a little model of the sphere. In this case it's going to be a basketball. It's simulating the sphere. And you can see that the arrangement is the sphere normally hangs from 3 trees by these vertical tethers which attach to the sphere right around the equator. Now what I've done for the purposes of strain testing the sphere is I have built a platform that's suspended from 2 long ropes that go up and over the top of the sphere to opposite corners of the platform. And then this rope goes from this corner of the platform up and over the top of the sphere to the far corner of the platform there. Now what I can do with these ropes and the platform is I can pile weights on the platform which applies a load to the top of the sphere, and you can see it stretches or applies tension to the tethers, which causes the tethers to get a little bit longer. And of course, in order to balance the forces, the strain or the stress on the tethers has to match.
Now let's look at the real strain test rig. This is a picture of the actual platform with a few weights hanging on it. You can see those are labeled in red text, and you can also see the green lines that represent the ropes that suspend the platform, and they go up and over the top of the sphere. The sphere and platform are being held up by a portable stand which is composed of 3 legs. Each leg is like a hockey stick with a horizontal blade at the top. The blades join at a hub in the center. You can see where the 3 blades come together. The sphere is held up by 3 chain tethers. Now the tethers attach at the top end to the joint between the leg and the blade of the hockey stick. There's a metal plate embedded in that joint. It's through bolted on both the leg and the blade end. And there are some extra holes drilled into that plate where I can attach the shackles that pick up the end of the chain. The bottom end of the chain tether attaches to a bracket on the shell of the sphere, and it's bonded to the shell of the sphere. A strain gauge has been inserted into the bottom of the tether between the bottom end of the chain and the attachment point on the sphere. These strain gauges measure the tension in the tether. They'll tell us how much force is being applied to the edge of the sphere. The tether is not exactly tangential to the sphere where it attaches at the bottom end. If you look at the bottom end of the chain tether, you can see that it's pulling out from the sphere at about a 10-degree angle. Now, since that is not tangential, it's putting an outward force on the skin at that point. The tether angle is not exactly vertical where it attaches to the leg at the top either. If it were vertical, it would be parallel to the leg, and then all of the force would be straight down the leg. However, since it's not, it means that the load on the tether results in both horizontal as well as vertical components. The vertical component causes compression in the post or leg, and the horizontal component results in a force down the blade to the blade of the hockey stick to the hub where the 3 hockey sticks join together. The horizontal forces cancel each other out where they come together in the hub. The purpose of the strain test experiment is to look for deformation or signs of strain in the sphere and or the legs as weight is applied. To do this properly, every time a weight is added to the platform, a series of measurements are taken, both inside the sphere and all around the legs. By recording these measurements and correlating them with the applied weight, we can get an idea of how much the sphere is moving with the amount of weight applied. Now here's a little video showing weights being added to the platform. We pick them up with a crane on the truck, and you can see from the video that the platform is wobbling around. It's floating, hanging from the rope, so consequently it moves every time he transfers his weight, or as the weight of the weights moves the platform.
4 weights on. There's the Tacuna software there. It's just telling me the strain on strain gauge 1 and
for strain gauge 2. I'm recording it. This is a graph that shows I've just added a weight. The weight was way over on the left side. So you can see it was a much more of an increase. That was me walking on the platform. And spikes there. Have a look at the door side strain gauge. Make sure it's still going. Okay, and bugger it. Okay, that's me walking on the platform again, door side. And the tension on that door side tether is 1,538 pounds.
Alright, this is a picture of the maximum weight.
Close to the ground but not touching. You can see it's moving around.
You can see that's the closest point to the ground, right in the middle where the sunspot is. And yeah, it is floating. There's quite a bit of flex in that lateral joist there. And as we say, we've got 4 50-gallon tubs full of water and 12 chunks of cast concrete that are approximately 650 pounds each. And so we'll go and total the strain gauges and get a number that will be somewhere in excess of 12,000 pounds.
Okay, so this is the strain gauges. You can see strain gauge 1 has got 3,665 pounds. Strain gauge 2 is 3,954. And strain gauge 3. What happened there? Strain gauge 3 has 4,429 pounds. Now, what has happened with these strain gauges is the weight I put on the platform down below was the maximum I could get. And right now what we've got down there is there are 12 concrete blocks. This is a little video of me taking some measurements inside of the sphere, again looking for deformation. The first measurement was from the South Pole up to the North Pole, and we didn't see any distortion at all in that measurement. It was pretty well consistently 3.3 meters and a little bit. And then I do a lot of measurements around the equator and a couple of diagonal ones as well. Other side. But what happens is where the chain comes in at an angle causes the well, if that was pulling the attachment point up, then we would expect that bolt to take an angle like that. So the attachment points certainly haven't let go at all with all that weight on them. Again, there's those screws on this one. You can see no bend on the attachment point, no lift on the screws. We'll go around the back. Okay, to sum up, we got a total weight on the sphere as measured by the force on the strain gauges as 12,950 pounds. And we couldn't detect any perceptible movement in the sphere. There was no distortion. All the measurements from very beginning to the very end of the strain test were within 2 millimeters, which is about as accurate as we could get with that laser measuring device. And the same on the legs. The legs didn't bend or move or distort in any way, shape, or form either. Have to try more weight next time. Anyway, we would like to say a very special thank you to Aaron and the guys at ABC Precast who contributed the weights that we used for the strain test. And thanks very much, Aaron. And that's all for us. Over and out.